Well, Islam Abdullah. So, any doubts from the last class? Yes, you can use your mic now. Any doubts from the last class?
No,
No,
sir.
sir.
No doubts. Okay. Fatma, you were absent in the last class. Did you went through the recordings?
Sorry, sir, I didn't get time to.
You didn't get time to. Okay. So, Fatma, in the last class, I have
Sir, I
started Gauss.
traveled to India. So
You traveling to India at this time?
I'm in India today.
This is the time to leave India. It's where exactly in India?
Yeah.
Where India? Where exactly in India? Which state?
Kerala.
Kerala. Oh, fine. Fine. Kerala is better than any other place. Okay.
Yeah.
That's the time to leave India. You're traveling back to India. Okay. So you are in Kerala now. Okay. So Fatma, up to last class, I have started electric flux. We have finished Gauss law. We have to do some numericals based on Gauss law only. So what is Gauss law, Sania? Yes, Sania. What is Gauss law? Sania, I'm audible. Sania is not in class. Huh? Mariam, do you remember what is Gauss law?
Yes, sir.
Yes. What's Gauss law?
Gauss's law states that the flux through a closed surface is 1 by epsilon 0
Hmm.
times the total charge enclosed by the surface.
Yeah, that's a Gauss law. Huh? If you have a closed surface and you place the charge inside that closed surface, then flux through the closed surface, which we calculate in this way, huh? Flux is integral of E dot ds. This comes out to be its q by epsilon naught only. This is Gauss law. This is how we calculate flux through a closed surface. Now we have two types of numericals in Gauss law. In the first type of numerical, you will have charge. He will give you charge and will ask you to calculate flux. For example, type 1 questions on Gauss law. You will have charge and you are supposed to calculate flux. It's like I give you a cube. It's a cube. This is a cube. This cube have 6 faces. I placed a charge at the center of the cube. This is the charge at the center of the cube. Now, can you calculate flux through the cube?
Yes, sir.
Calculate flux. Let's solve first part through cube. Second part, flux through each phase. Flux through each phase. So if I place a charge at the center of the cube, see, cube is a closed surface, huh? So you can use Gauss law for the cube. So the flux through the cube is just charge enclosed, which is q, divided by epsilon naught. This is the flux through the cube. It's charge enclosed by the cube divided by the epsilon naught. So phi is q by epsilon naught. The flux through the cube. Next, what we can do is we can calculate flux through each phase. So cube has 6 phases. Flux through all these 6 phases is q by epsilon naught. We need to calculate flux through a single phase. So we can solve this in this way. Say you have 6 phases in a cube. Flux passing through all 6 phases is q by epsilon naught. Flux through all 6 phases is q by epsilon naught. I need flux through one phase. See, this is charge. Electric field lines are passing through each face, all faces. Now since charge is placed at the center of the cube, so the flux passing through each face is same. So flux through all 6 faces is q by epsilon naught. So you can say that flux through one face, flux through one phase will be q by 6 epsilon naught. This is it. This is flux through one phase, which is q by 6 epsilon naught. Is it clear, both the parts?
Yes,
Yes,
sir.
Okay. Note it down. We'll do another question. Yes, can I change the slide now?
Yes, sir.
yes, sir.
Okay. So the same question is given in NCERT but in a different fashion. The NCERT says that you have a square. This is square. Each side of the square is a. Each side of the square is a. From the center of the square, from the center of the square, and at a height a by 2, I place a charge q. So we take a square, each side of the square is a, and from a distance a by 2 from the center of a square, I placed a charge q. You're supposed to calculate flux. You're supposed to calculate flux through the square. Flux through the square. Okay, so first of all, Amalia, can we use Gauss law for a square? Yes, Amalia. Can I use Gauss law for the square? Yes, no. Amalia, can I use Gauss law for square?
No, we can't
Why not? Why can't we use Gauss law for the square?
because it's not a closed.
Amalia, not audible, bache. Speak louder.
Because it's not a closed.
Yeah, because it's not a closed surface. So to use Gauss law for the square, you have to make it a closed surface. To make this a closed surface, what we can do is, yes, Abdullah, can you guess how can we make this square a closed surface? Abdullah Aslam.
Yes, sir.
Yes, how can we make this square a closed surface? Square is an open surface, no? Can you make this square as a closed surface? Or you can convert it into something which is a closed surface?
It's a cylinder.
No, we can't make slender out of a square. No.
We can
Make the
consider
cube.
it one of the faces of cube.
Yes, we can make it a cube. What we can do is we can add 7 more square to it. Let's add 7 more square to it.
The 5, right?
Sir, 5, right?
Sorry, yes, 5. Yes, 5. 5 more square to it and make it a cube. So we're adding 5 more squares to it and make it a cube. So if I make it a cube, it's like this is the same question. This is square of each side A, and this charge q is placed at a separation a by 2 from the center of the square. Now as soon as you place these 5 squares, you add the 5 squares into it, it get converted into cube, and this cube have a charge q at the center. So now you can solve it easily. Flux at the through the cube. Now you can solve it easily. Flux through the cube. Flux through cube is this cube epsilon naught. But this time you don't need flux through the cube. You need flux through the square. And what is square? One face of the cube. Okay, so first calculated flux to the 6 faces, which is q by epsilon naught. Then you calculated flux to the 1 face, which is q by 6 epsilon naught. Yes, Abdullah. Clear now?
Yes, sir.
Sania, Mariam.
Yes, sir.
Okay. Noted down. Fatma, are you getting it? No. Okay, just note it down. Okay, Fatma, see, you can, for Gauss law, we are calculating flux. Flux is just number of feed lines. If 4 feed lines are coming out of a surface, then we would say that flux is 4. Okay, I'm just giving you a summary of the last class. So if feed lines are coming out of the closed surface, then we will say that flux is 4. If this closed surface have a charge q, then the Gauss law says that flux coming out of this closed surface is q by epsilon naught. But for using Gauss law, the surface that you are using should be a closed surface. So what I did is I take a cube, which is a closed surface. I put a charge at the center. The flux through the cube is q by epsilon naught. Now this cube has 6 faces. So the flux passing through all 6 faces is q by epsilon naught. Then we need flux through one face, which is q by 6 epsilon naught. This is Gauss law of Atma, flux through one face. But you have to go through the recording of the last unit. Yes, have you written it?
Yes, sir. Done.
Yes, sir.
So both the parts have the same answer. Like the first one where you place the charge at the center of the cube, or the second one where you place charge at a distance a by 2 from a square. Both have the same answers. The answer is q by 6 epsilon naught only. So the same question, just different representations. Okay, if I give you another question. A charge q is placed at center of a hemisphere. Calculate flux through it. So I take a hemisphere and I place a charge q at the center of the hemisphere. Now, can you calculate flux passing through the hemisphere?
Yes.
Yes, what is the flux passing through the hemisphere? No, Abdullah, hemisphere is open. Hemisphere is like a bowl, an open bowl. Hemisphere is not a closed surface. You cannot use Gauss law directly. Yes, Ahmed, how will you make this a closed surface? This hemisphere is an open surface. How will you make it a closed surface? A symmetrical closed surface?
Add another hemisphere.
Yes, what we can do is we can add one more hemisphere. So when I will add one more hemisphere, what happens is it gets converted into a complete sphere. So you can say that add just one more hemisphere. So when you add one more hemisphere, it gets converted into a complete sphere. And the flux passing through this complete sphere will be Q by epsilon naught now. So you can say that flux through sphere is Q over epsilon naught. And this is sphere have two hemispheres, back to back two hemispheres. You can say flux through two hemisphere is Q by epsilon naught. And then you can say that flux through one hemisphere is Q by 2 epsilon naught. So this is it. Flux through sphere is Q by epsilon naught. Flux through two hemisphere is Q by epsilon naught. Flux through one hemisphere will be Q by 2 epsilon naught only. Is it clear?
Yes.
Yes.
Yes, sir.
Okay, just note it down. So these are a few questions in which you have a surface and a charge. You are calculating flux using Q by epsilon naught only. In the next series of numericals, you will have electric field and you are supposed to calculate flux using electric field now. So these three were one type of question, type A you can say. In these type of questions, charge is given. In the next series of numericals, electric field will be given and you will be supposed to calculate flux through the surface.
Done, sir.
Okay. After this, next question. This is basically a solid example of NCRT. A cube is given. Yes, the cube. This is x-axis and this is y-axis. This is y-axis. Okay, no, these are not x and y-axis. This is x-axis and this is y-axis. And this is the origin. Each side of the cube is A. The coordinates of this point is A. This x is equal to A. And there is an electric field which exists along x-axis E. The magnitude of electric field is alpha x to the power half. So the question says electric field, that's Ex, exists along x-axis calculate flux through the cube. And also the charge enclosed. So you have a cube. This is the origin of the cube. This coordinate is x equal to a. The size of the cube is a. You're supposed to calculate the flux through the cube and also the charge enclosed. See, Ex is given, Ey and Ez are 0. So there is no electric field along y or z axis. Electric field exists only along x axis. There is no component of field which is along y axis or z axis. There is only one component of field which exists along x axis only. So let's solve it. When I solve it, see, to solve these type of problems, I don't have charge, so I cannot use q by epsilon naught. So what we do is, whenever we calculate flux through the cube, we divide this cube into number of faces. We divide this cube into a number of faces. Like this is phase 1, this is phase 2, or I will name it like this is the left face, this is the right face, this is the top face, this is the bottom face, this is the front face, and this is the back face. So we divide cube in 6 phases, then we will calculate flux for each of the phase one by one. So it's a lengthy question, usually comes in 5 marker questions. So first of all, let's calculate flux for the left phase. Flux for, okay, this is right. For the right phase, and this is the left phase. Flux for the right phase. Okay, Noor, what is the direction of this phase? X-axis, Y-axis, Z-axis. What is the direction of this phase?
Towards positive x-axis.
Towards positive x-axis. Why is along positive x-axis only?
Because it's perpendicular to the
It's because the direction of area vector is outwards normal. So the outwards normal to this face will lie to the right hand side. So this is the direction of this face, which is along x-axis. Two back faces. No, it's a bottom face and this one is the back face. Abdullah, it's a cube, na, a 3-dimensional object. So this is the bottom face and that is the back face. And this is the bottom. So for the right face, this is the direction of area vector and this is the direction of electric field. So when I calculate flux for the right face, I will use flux is, see, right face is a curved face or a plane face? Sania, this right face is a curved or a plane face? Square?
It's a plane.
It's a plane face. So I can use flux in this way, E dot S only. That's my first equation. Shahzada, how much is, what is the area of this face? Each side of cube is A. What is the area of this particular face? This face? Shahzada?
Yes, sir.
What is the area of this face? Each side of the cube is A.
It's also a
What is the area? A is the side. I'm asking about the area of this face.
side into side.
Side into side. That's A square. Huh? That's equation number 2. And what is the direction of this face? It's along positive x-axis. So I can write this area vector is A square I cap. That's second equation. Now I need field. Field is given as alpha x to the power half. And this field is along x-axis. That's why I'm using I cap here. Okay, what is the value of x coordinate for the right face? Mariam, what is the x coordinate for the right face? See, each face will have different values of x coordinate. What is the x coordinate for the right face?
A.
A. Here to here is also A. And the right face is here. X coordinate means separation from the origin.
X minus A.
No.
Sir, 2A.
2A. This is A and this is again 2A, right? See, x coordinate is simply the separation from the origin. Now, from the origin, the separation of this face is A and this side is also A, so the total sum up will be 2A. So you can say that X is equal to 2A. That's equation number 3. Okay.
Yes, sir.
So we can substitute this. Basically, this alpha x to the power half is a non-uniform field. This field will have different values for different values of x. So when we are calculating field for the right phase, I need x coordinate for the right phase. For the right phase, the x coordinate is 2a. So I can substitute this 2a here. When I substitute this 2a here, the electric field for the right phase will comes out to be alpha into 2a to the power half I cap. So I can just write this as electric field for the right phase is alpha, power half means root. It's root 2 into a to the power half I cap. That is equation number 4. So what and this is electric field for the right phase only. So this is how we calculate flux for the right phase. I need electric field and area vector. This is the area vector and this is the electric field. Now I can substitute 2 and 4 in 1. So when I substitute 2 and 4 in 1, I will get flux for the right phase is ER. ER is alpha root 2 a to the power half I cap dot area vector, which is a square I cap. So I can further write this as flux for the right phase is alpha root 2. See, this a square is not a vector, it's just a number. You can multiply it with this a to the power half into a square. Yes, Sania, how much is a to the power square and a to the power half? A square and a to the power half, if I multiply them. What is the final power of a, Sania?
Half.
Half. Half and a square. When you multiply them, powers get added up. How much is it? Sania.
What?
How much? Sania, take LCM. 2,
Okay.
then 1 plus 2 to 4, 5 by 2.
Oh,
Yeah?
okay. Yes.
5 by 2, I cap. Not I cap. Then this is I cap dot I cap. And what is I cap dot I cap, Sania? We revised this in the last class only. What is I cap dot I cap?
X-axis.
How much?
X-axis.
No. What is dot of I and I? Yes, it's 1. Sania, just turn the pages. In the last class, we have revised dot product. I mentioned there that I cap dot I cap is 1.
Yes, sir.
So this is the flux for the right phase, which is alpha root 2 a to the power 5 by 2. That is my equation number 5. In the same way, we have to calculate flux for each of the individual phase. When the field is given and you have a cube and you are supposed to calculate flux for the cube, then what you will do is you will be calculating flux for each of the individual phase differently. So first I calculated the flux for this phase, right phase. Now let's calculate flux for the left phase. Flux for left phase. For the left phase, I will write this as flux is electric field at the left phase dot area vector. I call this as equation number 6. We know that area is a square. Now who will tell? Abdullah, what is the direction of left phase? Right, left, positive x-axis, negative x-axis. What is the direction of this phase, Abdullah?
Minus I cap.
Minus I cap. Very good. The direction of the left phase is outwards normal. So outwards normal is to the left hand side. This is the direction of left phase. So I can use this minus I cap here. It's a square minus of I cap. So this is the area vector. So your area vector is minus of a square I cap. That is equation number 7. Next, let's calculate field. The electric field is alpha x to the power half. Ahmed, what is the x coordinate of the left face?
Semi.
How much? X coordinate of the left face. How much is the x coordinate of the left face, Ahmed?
A.
A, yes. See, this is the left face, huh? The x coordinate of the x face is x equal to a only. So here you will put x equal to a, and there is 1 root 2 also, no? No, alpha x to the power of 1. So a only. So when I put the value of a, the electric field will be alpha x, not x, a to the power half. It's not minus, it's I cap. That's equation number 8. Abdullah, electric field is always along x-axis. Electric field is along x-axis always. Field is always along x-axis, it's given. We just have to decide the direction of the phase. Now when I substitute 7 and 8 is 6. Then flux for the left phase will be, it's alpha a to the power half I cap dot minus of a square I cap. So flux for the left phase is, I can take this minus sign outside. This is alpha. Then it's a half plus 2 is 5 by 2. It's I cap dot I cap. See, I cap dot I cap is 1. So the flux for the left face is minus alpha a to the power 5 by 2. It's equation number 9. So now we know flux for the left face also. Is it clear up to this equation number 9?
Yes, sir.
Yes, sir.
See, if you have a cube, then you have to calculate flux for each of the individual face now. So we have finished with the right face and the left face. Then we will move on to the top face. Mariam, what's the direction of the top face?
So towards y-axis.
Towards y-axis. Perfect. This is the direction of top face. Y-axis. J cap. Okay, Mariam, what is the angle between this area vector of the top face and the electric field? Because the electric field is along x-axis always.
It is perpendicular.
Perpendicular. See, electric field is always along x-axis. Now for the top face, area vector is upwards. So the angle between them is 90 degree. So I can write in this way, flux for the top face is its electric field, area vector into cos 90. Right? It's E dot S basically, na? So I can open the dot product in this way also. This is ES cos 90. Your flux will be 0. Is it clear why the flux for the top face is 0?
Yes, sir.
Yes, yes.
Because top face is perpendicular to field. Okay, Amalia, what is the direction of this bottom face? The bottom face of the cube?
Negative y.
Where?
Downwards.
Downwards, negative y-axis. It's minus of j cap. And again you can see that electric field and area vector are perpendicular to each other. So for the bottom face also, the flux will be 0. So I'm writing it here only. Okay, Shahzada, what is the direction for the front face? This face of the cube.
So it's coming front, so z-axis.
Yeah, it's coming outwards, no?
Yeah.
Front face is this, so it's coming outwards, out of the plane of the copy, or it's out of, if you are viewing this thing in a laptop, it's coming out of the laptop. That's z-axis. So if it is along z-axis, then again it's perpendicular to x-axis, so it's perpendicular to field now. Yes, Ahmed, you are right. So for the front face also, it's 90 degree. If I take for the back face, then for the back face, direction is inwards. Inwards means negative z-axis, which is again perpendicular to x-axis. Top, bottom, front, back. So for all faces, net flux is 0. That is equation number 10. Is it clear, everyone?
Yes,
Yes,
sir.
sir.
Very good. So this is how we calculate flux for the top phase, for the bottom phase, front phase and back phase. Next what we can do is we can calculate total flux. For the total flux, we will add all the individual flux. We will add flux due to left phase, we will add flux due to right phase, we will add flux due to top phase, flux due to bottom phase, flux due to front phase, and then flux due to back phase. So the total flux will be all, the rest are is 0. For the right phase it was alpha root 2a to the power half. For the left phase this is minus alpha a to the power 5 by 2. For the right phase this is alpha root 2 a to the power 5 by 2 and the rest is 0. So the total flux is, I can take this alpha a to the power 5 by 2 as common. When I take them as common, I am left with minus 1 and root 2. So now I get that alpha is phi is alpha a to the power 5 by 2, it's minus 1 plus 1.4. So your phi will be, it's alpha a to the power 5 by 2, it's 0.4. So you can say that this is 0.4 alpha a to the power 5 by 2. This is the final answer. Yes, is it clear?
Yes, sir.
So if you have a cube to calculate flux using electric field, then it's a very lengthy problem. It's usually a 5-marker question. Okay, now note it down and tell me if you still have any doubt. Okay. Can I change the slide?
Yes, sir.
Everyone have written, huh?
Yes, sir. Yes, written. Yes, can I change the slide now? Sania, Abdullah.
Yes.
Yes, sir.
Okay, so everyone have written, huh? So that's the first part. This is how we calculate flux. For the second part, you're supposed to calculate the charge enclosed. So Noor, can you tell me how would you calculate the charge enclosed?
The flux is equal to charge by
Yes. Now I can use Gauss law. Huh?
yes.
Now I can use Gauss law. I can say that flux is its Q enclosed divided by epsilon naught. So I can write that Q enclosed is flux multiplied by epsilon naught. So I can write that Q enclosed is flux, which is 0.4 alpha a to the power 5 by 2, 0.4 alpha a to the power 5 by 2 into epsilon naught. This is the charge enclosed by the closed surface. So always remember, if you have a cube and you're supposed to calculate flux, then divide this cube into 6 faces, calculate flux due to each of the individual phase, and then add them up. This is for the cube. Just note it down, then we will move on to the next question.
Sir, done.
Done. Okay, good. After cube, the next shape is cylinder. Now we'll see how to calculate flux through a cylinder. This is again a solved example of NCERT. So you have a cylinder. This cylinder is given. Abdullah, since value of alpha is not given, so I cannot substitute them. But if in the numerical the value of alpha and a is given, then yes, obviously then you will substitute them. If it is given, then you will substitute them. In this question, I have not given the value of alpha and a, so there's no point of substitution. Okay.
Okay, sir.
So this is your cylinder. This is the cylinder. This is axis of the cylinder. This is the y-axis. This is the x-axis. This is origin. The length of the cylinder is L. Total length of the cylinder is L. This is the total length, which is L. This origin is just at the center of the cylinder. That means this length is L by 2 and this is also L by 2. This is L by 2. This is also L by 2 and this is L. Electric field exists in the cylinder in this way. Like this is your field. At the right of the origin, your field is along positive x-axis. To the left of the origin, the field is along negative x-axis. So the direction of field is changing. So to the right of origin, this is your field E, which I am writing as E naught I cap. And to the left of origin, your field is E. Magnitude is E naught only, but the direction is negative x-axis, so I'm writing it as minus I cap only. The radius of the ends of the cylinder, this radius is R. So suppose to calculate flux through the cylinder, as shown in figure. This is the flux through the cylinder as shown in figure. So we can divide this cylinder into 3 categories. This is end 1, this is the curved surface, and this is the end 3. For the first end, this is the direction of area vector, which is along x-axis. This is electric field. Electric field and area vector are acting in same directions. Or I should write this as I cap. Okay, I'm also writing the field here. Electric field is given in this way. Although I have mentioned the electric field in the diagram, but it is given in this way. Electric field E is E naught I cap for x is greater than 0, and the field is E naught minus I cap for x is less than 0. This simply means if you move to the right of origin, then your field is E naught I cap, and if you go to the left of origin, then your field is minus of E naught I cap. Now you are supposed to calculate the flux. Now, just like a cube, when we calculate flux through a cube, we divide cube into 6 faces. But when we calculate flux through a cylinder, we divide this cylinder into three parts. We divide this cylinder into two ends, end 1 and end 3, and a curved surface which is end 2. So remember, always remember this statement that divide cylinder into two ends and one curved surface. So we can divide this cylinder into two ends and one curved surface, and then we can calculate the flux. So let's first calculate the flux through end 1. As I have already mentioned, the direction of this end 1 is to the I cap, positive x-axis. So for the end 1, I am writing this as the flux is E dot S. That's my first equation. If anyone need the value of E, then the value of E is E naught I cap. That's my second equation. If you need area vector, then area vector is pi r square I cap. That is the third equation. So we can substitute 2 and 3 in 1. When we substitute 2 and 3 in 1, what I get is flux through end 1 is, it's E naught I cap dot pi r square I cap. So I can write this as E naught pi r square. It's I cap dot I cap. And what is I cap dot I cap? It's 1. So this is the flux through the end 1, which is E naught pi r square only. That's my equation number 4. So that's the first thing. Just like phase 1, we can calculate flux through this end 2. Sania, what should be the direction of this second end, this one?
Inward
Where?
to outward.
Outwards. And where is this outwards? X-axis, positive x-axis, negative x-axis, y-axis. Where is the outwards?
Negative x-axis.
Perfect. Negative x-axis. This is the direction of area vector minus of I cap. So for N2, we can calculate flux in this way. Flux is electric field dot area vector, that is equation number 5. How much is electric field for the second end? That's minus of E naught I cap. Okay. This is second Abdullah, okay, and the third is the curved surface. That's E dot S. We can write that E, electric field E here is E naught, see, minus I cap, that's the value of electric field. That is equation number 6. And the area vector is pi r square minus I cap, that's equation number 7. So what we can do here is, we can just substitute the values of 6 and 7 and 5. When we substitute the values of 6 and 7 in 5, we will get that flux for the second end is, how much is E? This E is E naught minus I cap. How much is S? S is pi r square minus I cap. It's E naught minus I cap dot pi r square minus I cap. So flux through the second end is, it's E naught pi r square. I cap dot I cap is 1. So I can write this as equation number 8. So that's E naught pi r square. Is it clear? Flux through the end 1 and then flux through end 2.
Yes, sir.
Okay, so Now Shahzada will tell. Shahzada, can you expect what is the value of flux for the curved surface? Shahzada,
Yes, sir.
what is the value of flux for the curved surface, for this curved surface?
So it was Q by epsilon naught.
No. Just
So
for
it
the
was.
curved surface.
So it was
Hmm.
uh, that delta one. What we say?
Yes, Ahmed, you are correct. You are saying, Shahzada, it should be integral of E dot ds, huh?
Yes, sir. Integral. Yeah.
Integral of E dot ds, okay. Mariam, can you guess what is the flux to the curved surface? Yes, Ahmed, Noor, Abdullah, you all are correct. Yes, Mariam, can you guess the flux to the curved surface?
You mean the value?
Yeah.
Area of cylinder.
No. No, no, no. See, if I take, this is curved surface, huh? I want to calculate flux for the curved surface. For the curved surface, what we will do is, we will take area vector which is perpendicular to the curved surface, and then we will take the dot product of that area vector with the electric field. Flux through curved surface. For the curved surface, the flux is integral of E dot ds. Amalia, what is the angle between electric field and area vector? Electric field is along x-axis.
90 degree.
90 degree, right? Electric field is along x-axis and your area vector is perpendicular to x-axis. So angle is, when I open this dot, this will be EDS cos 90, so your flux will be 0. That's equation number 9. So Abdullah, Noor and Ahmed all were getting 0. So flux is 0. So for cylinder, we always divide cylinder into 3 parts, 2 ends and 1 curved surface. We will calculate flux for each part separately. Then we will calculate the total flux. Huh? And that total flux will be phi 1, phi 2, phi 3. Phi 1 is E naught pi r square. Phi 2 is E naught pi r square. Phi 3 is 0. So the total flux is 2 E naught pi r square. That's equation number 10. Okay, Abdullah, if I ask you to calculate charge enclosed by the cylinder, then what will you do? How will you calculate the charge enclosed by the cylinder? Abdullah.
Sir, phi is equal to Q enclosed by epsilon.
Yeah, yes, very good. We will use Gauss law to calculate charge enclosed. Gauss law says phi is Q enclosed divided by epsilon naught. So we can write that Q enclosed is phi multiplied by epsilon naught. That is equation number 11. So we can just substitute 10 in 11. So the Q enclosed is now phi, which is 2 E naught pi r square into epsilon naught. So these are two very important examples on flux. So when you have field, you calculate flux for a cube, you divide cube into 6 parts. When you calculate flux for a cylinder, you divide cylinder into 3 parts. This is it. Note it down, then we will start some derivations. These are lengthy but very important numericals on Gauss law. Tell me if you still have any doubt. It's okay. See, in first chapter, the most important topic is Gauss law. The topic that have maximum weightage in the first chapter is Gauss law. The weightage of electrostatics is around 8 marks. Out of 8 marks, 3 is reserved for Gauss law. So there's 70 to 80% chances that you will get a 3 marker or a 5 marker question from Gauss law. It's most important topic of first chapter.
But the value of epsilon 0 are not same.
Value of epsilon naught. Why I'm not using the value of epsilon naught? That's what you're saying?
Yes, sir. No,
This
I
value.
mean this over here and here.
Okay, okay. No, this is E naught and this is epsilon naught. This is E naught, field. See, the electric field is given in this way. Electric field is given as E naught. So one is E naught, another is epsilon naught, okay?
Yes, sir.
And I'm not substituting the value of epsilon naught because numerical value is not given. You don't have numerical value of R, you don't have numerical value of E naught. So there's no point in substituting the numerical value of epsilon naught. There's no point in it. Yes, yes, Fatma.
Thank you, sir.
Okay.
Sir, done.
Okay. Okay, so after this, the next is, so these are the types of numericals that you can usually get on electric flux and Gauss law. The next are few derivations. So before starting with derivation, I want to discuss one geometrical concept, and that is known as Gaussian surface. Gaussian surface is basically a topic of geometry. Gaussian surface are some geometrical surfaces which we use to simplify this integral. See, when you are integrating E dot ds, you are integrating over some surface. There are certain surfaces for which this integral is very simple. There are certain surfaces which can simplify this integral. Those surfaces are known as Gaussian surfaces. So Gaussian surfaces are some geometrical shapes used to simplify closed integral of E dot ds. So these are few geometrical shapes which we use to simplify this particular integral, which is closed integral of E dot ds. This is what we call as Gaussian surface. So there are certain criteria to choose a Gaussian surface. Criteria to choose Gaussian surface. The very first criteria is it should be closed. If it is not closed, that means you cannot use Gauss law. You can use Gauss law only if these surfaces are closed. So Gaussian surface should be closed surface. Second, electric field, not electric field, electric field should be parallel or perpendicular to the surface. So field should be either parallel to the surface or it should be perpendicular to the surface. See, this condition will help you in opening this dot product. So if field is parallel, that means your cos theta will be 0. And if your field is perpendicular, then your theta would be 90 degree and your flux will reduce to 0. So the second criteria will help you to open this dot product. Then we have third criteria which says that field is uniform. See, if this field is uniform, then you can take it outside the integral. So the uniform field, what you can do is you can just take this field outside the integral. You can just take this field outside the integral. This is how we solve it. So to choose Gaussian surface, we follow these three criteria. That first one, it should be closed. Second one, electric field should be parallel or perpendicular to the surface. And the third one, electric field should be uniform. It should be uniform throughout the surface, E dot ds. Just tell me, is it clear?
Yes, sir.
Okay, good. Note it down, then we'll start the next thing. Written?
Yes, sir.
Okay. Everyone, can I change the slide now?
Yes, sir.
Sure.
Yes, sir.
Yes, sir.
Okay, after this Gaussian surface, what we can do is we will calculate electric field due to some symmetrical charge distributions. When I say symmetrical charge distribution, that means we can have three types of symmetrical charge distribution. You can have a linear charge distribution. In linear charge distribution, charge is distributed over a wire. You can assume it as a wire. Say you have a wire, very long wire, you distribute some charge over the wire. That's first type of charge distribution, which we call linear charge distribution. The second type of charge distribution could be a surface charge distribution, where charge is distributed over a surface. That you can assume, like if you have a wall at your home, if you distribute some charge over the wall, then that particular distribution is surface charge distribution. You can have third charge distribution, which we call volume charge distribution. So if charge is distributed throughout the volume, like if you take a sphere, you distribute charge throughout the volume of the sphere, even in the material of the sphere, then the charge distribution is what we call as the volume charge distribution. These are the three types of charge distribution that we will use here: linear charge distribution, surface charge distribution, and volume charge distribution. So let's first study these charge distributions, then we will calculate the field due to it. So let's first study continuous charge distributions. What are the three types of charge distributions, Sania?
Linear
Hmm.
and other two I did not miss it.
Other two we do not remember. Ahmed, what are the
Surface
three
and
types?
volume.
Linear, surface, and volume. So let's first start with linear charge distribution. linear charge distribution. So in this charge distributions, I will use a word which is uniform. So first understand what does uniform means. I'm giving you two types of surfaces. On first surface, I distribute charge evenly, everywhere, it's evenly. And for second, I distribute charge in this way. So which distribution is uniform? First one or the second one?
First.
Person.
First one. The uniform is, now you get what is uniform. Uniform means charge is distributed equally. Everywhere you will have same amount of charge, then the distribution is uniform. But if the distribution is not equal, charge is not equally distributed, then you will say that it is non-uniform distribution. So linear charge distribution, I take a wire. This is a wire, a one-dimensional wire, and I distribute charge uniformly on this wire. Charge is uniformly distributed over this wire. The length of the wire is L and the charge of the wire is Q. So I will say that charge Q is uniformly distributed on the wire. So we distribute a charge Q over the wire. Okay, so here we first calculate linear charge density. We first calculate linear charge density. We represent this charge density as lambda. Linear charge density simply means it's charge per unit length. Linear charge density is charge per unit length. This charge per unit length is known as linear charge density. We represent this linear charge density with lambda and we write this as this is the ratio of total charge and total length of the wire. This ratio of total charge and total length of the wire is known as linear charge density. This is the linear charge density. Lambda is total charge over total length. Okay, the SI unit is coulomb per meter. The SI unit of linear charge density is coulomb per meter. After linear charge density, next what we can have is surface charge density. No, not yet surface charge density. We can have some more cases in linear charge density. See, instead of the whole wire, if you have information about a small portion of the wire only, like instead of knowing the total length of the wire, you just know the length of this portion. That's delta L. Instead of knowing the total charge on the wire, you know charge on this section only. That's delta Q. Using this, you can also calculate linear charge density that we can write as it's delta Q over delta L. That's linear charge density. That's delta Q over delta L. This is linear charge density here. Okay?
Okay, sir.
Okay. Now, we can do one, but the issue with both these expressions is this expression is valid only if your charge density is uniform. We can use this expression again only if your charge density is uniform. We cannot use these expressions for a non-uniform charge density. For a non-uniform charge density, what we did is, non-uniform means if charge is not equally distributed. For non-uniform charge distribution, we can write it as lambda is, I'm taking this limit delta L tends to 0. Like I'm shrinking this length element, to a very, very small value. Delta L tends to 0, it's delta Q over delta L, which is dq over dl. So this is lambda, which is dq over dl now. This is the linear charge density lambda, which is dq over dl now. This expression is important. This you can use for non-uniform also. If your charge distribution is non-uniform, then also you can use this expression. So these are the three types of distributions, three types of expressions for linear charge distribution. In the first expression, I am using total charge and total length. In the second part, I am taking a small part of the wire and the charge over it. In the third part, it's extremely small element. So we can use the last definition for non-uniform distribution also. Just note it down, then we will move on to some numericals. And tell me if you have any doubts in this discussion. Sure. Yes, can I change the slide now?
Yes, sir.
Okay, perfect. Let's do with this very basic numerical on linear charge distribution. Charge of 10 coulomb plus 10 coulomb is uniformly distributed on a wire of length 5 meter. Okay, so you have a wire, the length of the wire is 5 meter and the charge of 10 coulomb is uniformly distributed over it. Calculate first part. Linear charge density. Second part. Charge on 2 meter length of wire. So you have a wire. This wire carries a charge of 10 coulomb and the total length of the wire is 5 meter. You're supposed to calculate the linear charge density of the wire and the charge on 2 meter length of the wire. Solve it. Okay. Yes, Abdullah, first part is correct. Sania, first part is correct. Shadaza also first part is correct. Yes, Noor, you're correct. Abdullah, second part is also correct. What about the rest? Mariam, Amalia, Ahmad?
So we have to type the answer.
Yes, you have to type the answer, please. Yes, Amalia, first is correct. Mariam, Fatma? Fatma, this is a fresh topic, huh? This is fresh topic. This linear charge density is a fresh topic. Amalia, first is correct, but I think you're making some mistake in second part. Yes, Ahmad, first is correct. What about the second one? Yes, Fatma, first part is right. No, second is wrong here. Mariam, first is correct. Shazada, second is wrong. Why are you getting 5? Yes, Ahmed, now you are right.
So I just gave one answer, I mean.
Okay. Amalia, second part is right. No, Shazada. No. The second part, you're supposed to calculate the charge, not the charge density. Okay, I'm solving it. First part is, everyone is doing correct for the first part. No, Sania, not 20. See, the total length of the wire is 5 meter. The total charge on the wire is 10 coulomb. So your lambda is simply total charge over total length. So it's simply charge is 10, length is 5. So this is simply 2 coulomb per meter. That's lambda. You can write this lambda in this way also, that this is delta Q over delta L. You can write delta Q as lambda into delta L. You can write delta Q as lambda. How much is lambda? Lambda is 2. And how much is delta L? This is the first part. This is the second part. Delta L is this. See, you know charge on 1 meter. See, the second is straightforward. You know charge on 1 meter. The charge on 1 meter is 2 coulomb. Then how much is charge on 2 meter length? You just simply multiply it. You will multiply it by 2. It's unitary method. Charge on 1 meter is linear charge density. That's 2 coulomb per meter. Then asking what is charge on 2 meter length? That should be 2 into 2, which is 4. Is it clear, everyone?
Yes, sir.
Yes,
I'm
sir.
just using unitary method, nothing else. I'm saying the charge on 1 meter length is 2 coulomb. Then the charge on 2 meter length should be 2 into 2. It should be 2 into 2. And the charge on 2 meter length should be 4 coulomb. This is the charge on 2 meter length, 4 coulomb also. So this is how we calculate charge. Okay, just note it down, then move on to the next topic. Everyone, is it clear? Because I'll be using this in the next derivations.
Yes, sir.
Yes,
Okay, I'm giving you another example. Okay, so you have a wire. The linear charge density of the wire is this. Lambda is equal to 2x. That's the linear charge density. You're supposed to calculate charge on 10 meter length of the wire. So we can start this question in this way, that lambda is its dq over dx. This is linear charge density lambda, which is dq over dx. We can write this dq as lambda dx. See, the charge density is not uniform. The charge density is non-uniform now. So for the non-uniform charge density, we will be using this relation. But instead of del, we will use appropriate variable. See, your lambda is a function of x, so I will use dx. So see what this dx exactly means. So you have a wire of length 10 meter. I'm taking a very small section of the wire. The length of this small section is dx and the charge over this small section is dq. We have revised integration in this batch? Yes or no?
No,
yes, sir.
We have not yet revised integration. Okay, we'll do it later. We'll first revise integration, then we will come to the solution of this thing. Well, if someone is comfortable with the integration, then I'm just completing this thing. dq is lambda dx. I can write q as integral of lambda dx. I will revise integral in the next lecture. Lambda dx. Just remind me to start next lecture with the revision of integration. So we can write this as 0 to 10. Lambda is 2x dx. When we integrate it, we can take this 2 outside. Integral of x is x square by 2. Limit is 0 to 10. So 2 will cancel this 2. Your q comes out to be 10 square minus 0 square. Your q comes out to be 100 coulomb. So this is the charge, 100 coulomb charge. This is the 100 coulomb charge over this wire. Just note it down, then we will move on to the next topic. If you don't remember integration, then don't worry. I will revise integration in the next class. I have written the question, that's why I just complete the solution, but I will revise this topic in the next class. Is it clear? Are you getting the difference between the linear and the non-uniform? Uniform and the non-uniform case?
Yes,
Yes,
sir.
sir.
For non-uniform cases, you will use integration. You will need integrals. Okay, so fine. So can I wrap it up?
Yes, sir.
No, sir. Okay, just note it down. Then we will study the second type of charge distribution, surface charge distribution.
Done, sir.
Okay. So can I change the slide now?
Yes, sir.
Yes, sir.
Sure. Okay. The next thing is surface charge, surface distribution. So if you know linear charge distribution, then you can easily guess surface charge distribution. Instead of length, I am using area only. The rest, all things are same. So area is S. Over this area, some charge Q is uniformly distributed. Charge Q is uniformly distributed on the surface. So you have a surfaces. Over the surfaces, some charge Q is uniformly distributed. So we can calculate surface charge density. This is not charge per unit length, this is charge per unit area. So we are calculating surface charge density. We represent it by sigma. This is charge per unit area. Instead of lambda, I will use sigma. Instead of L, I will use A, sigma, and here I will use this thing. The unit will change. Sigma is charge over area. Sigma is charge over area. Unit is coulomb per meter square. Instead of lambda, we will use S, we will use S, we will use S, we will use lambda. Sigma is delta Q by delta S, which is dQ over ds, which is dQ over ds, which is equal to sigma. Yes, is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
So instead of length, we are just using area. So surface charge distribution is just charge divided by area. Note it down, then we'll do some numericals on this concept also. This is the second type of charge distribution. Then we will discuss volume charge distribution. So, okay. Okay, now let's do this simple problem.
So not done.
Okay, not yet done.
Yes, can I change the slide now?
Yes, sir.
Yes.
So you have a charge of 10 coulomb uniformly distributed on the surface of a sphere of radius, let's say 2 meter is the radius of the sphere. Calculate first part. This area of the sphere is 4 pi r square. Huh? This is radius, not the area. Calculate first. Surface charge density. Second, charge on 2 meter square area. Next, you need I just calculate charge on 2 meter square area of the sphere. Solve it. Then we will start volume charge distribution. Calculate and report your answer in chat room. Don't substitute the value of pi. You can leave your answer in pi only. Yeah? Don't put pi equal to 3.14. That will make your calculations lengthy. Okay. Yes, Abdullah, you're right. Yes, Shazada, you're correct. Right, Abdullah, you're right. Mariam is correct, but Ahmed, I think you're making some mistakes. Just check your calculations once more. The first part, na Ahmed? Yes, it's wrong.
Yes, sir.
It's wrong, wrong. Shahzada, the second part of the answer?
Yes, sir.
Area is 2 meters square, so no, you're wrong. No, Shahzada, it's not correct. Yes, Noor, first part is correct.
Says the area for a circle is 22 pi r square, right?
4 pi r square. It's not a circle, it's sphere.
Sphere, okay, sir.
Noor, first and second both are correct. Fatma, is it first part or second? Sania, is it first part or the second one?
Yes, sir. First part.
No, bacha, you put the value of pi, okay? See, the total charge on the sphere is 10 coulomb. Radius of the sphere is 2 meter. Surface area is 4 pi r square. So the surface area is 4 pi into 2 square. So the surface area is 16 pi meter square. So for the first part, we can just simply get the ratio. Sigma is charge upon area. So the charge is 10 coulomb. Area is 16 pi. So your sigma comes out to be 5 by 8 pi. Fatma, Sania, is it clear?
Yes, sir.
Okay.
Sir, we cannot substitute the value of pi.
Even you will substitute, so it will be 3.14. Huh? Even in that case, it won't be 1.96, it will be less than 1.
Okay.
Second is I can write this sigma as delta Q over delta S. So I can write this delta Q as sigma delta S. Delta S is 2 meters square here. Sigma is 5 by 8 pi. So I can write delta Q as it's 5 over 8 pi multiplied by 2. It gets cancelled out. It's 4. So delta Q is 5 by 4 pi coulomb. 5 by 4 pi coulomb is delta Q. This is the charge. 5 by 4 pi coulomb is the charge on the sphere. Correct?
Yes,
Yes,
sir.
sir.
Okay, just note it down. Then we'll do the last type of charge distribution, that's volume charge distribution. Okay. Next. After surface, so everyone have written?
Yes.
Yes, sir.
Surface, linear, the next surface, next is volume charge distribution. So here, charge is distributed on a three-dimensional volume. So you can say that this is a cube, a three-dimensional object. Charge Q is distributed over it. Charge is Q, volume is V. Is uniformly distributed on the volume V. So instead of area, I will include volume only. Volume charge density, charge per unit volume. I will not use sigma, I will not use S. Unit will change, sigma will not come, S will not come, sigma will not be there, S will not be there, S will not be there, sigma won't be there. So charge Q is uniformly distributed on the volume V. Next, what I need is I need volume charge density, which is rho. This is charge per unit volume. Rho is Q over V. Rho, the same as that of density, Abdullah. Rho unit is coulomb per meter cube. Charge by volume. For uniform charge density, rho is delta V tends to 0, delta Q over delta V, dQ over dV, dQ over dV is rho only. So this is volume charge density. If the charge is distributed over a three-dimensional volume, then we use rho, which is dQ over dV only. Is it clear?
Yes, sir.
Okay, just note it down. Then we'll do one numerical on volume charge density.
sir, finish.
Finished. Okay. Let's do one last numerical of this class. Charge of, let's say, 10 coulomb is uniformly distributed throughout the volume of a sphere of radius 3 meter. The volume of the sphere is 4 by 3 pi r cube. Calculate first part. Oh, first of all, calculate charge, not charge, volume charge density. First, calculate volume charge density. Second, calculate charge on, let's say, 3 meter cube volume of sphere. Solve it and report your answer in chat room. Do it. So, okay, Abdullah got some answer. 5 by 18. Okay. Okay, just keep reporting your answer, then we will calculate it. Okay, let's calculate it together. We don't have much time left. Okay, I'm calculating. Yeah, rho is charge over volume. So how much is charge? Charge is 10 cube. How much is volume? It's cube. Huh? Sphere 4 by 3 pi r cube. So we'll be left with 10 by square 936 pi. So that's 5 by 18 pi coulomb per meter cube. Then for the second part, I can write that rho as delta Q over delta V. So we can write that delta Q is rho into delta V. So we get delta Q is rho. Rho is 5 by 18 pi multiplied by delta V. And how much is delta V? That's 3. 3, 6, 18. So it's 5 by 6 pi coulomb. Clear, everyone?
Yes, sir.
Yes,
So
sir.
these are the 3 types of charge densities. In Friday class, I will use these charge densities. Huh? I'll be using them. So hopefully Friday will be the last class of first chapter. I'm left with just 3 derivations, and then we will move on to second chapter in the next week. So let's stop here. If you have any doubts, we can discuss it right now.
Thank you, sir.
Okay, love it.